When you work on a rocket, you will most likely deal with many components and subsystems. The thermodynamic cycle, the involved turbomachines like pumps and turbines and their performance, secondary flow systems which affect the leakage flows, bearings and their cooling and lubrication mechanism, and many more. All of these are connected and influence each other. So how do you bring all these pieces together to have a complete view of your entire system and ensure correct operation and performance prediction for any conditions? Holistic modeling is, as we call it, is the approach to link the various subsystems and components together. So let me show you an example of this. Here's an example of a rocket cycle engine that we recreated inside of AxSTREAM system simulation. We are coupling the system level modeling, which is done by these 0D elements here, with the geometry-based turbomachine solvers to predict the turbine and pump's respective performance. The 1D elements here can be used to simulate flow through a piping system or cooling channel. So we have the turbine element connected to the turbine geometry, the fuel pump connected to the geometry as well, and so forth. The idea is then that the cycle is being calculated for the different cases, including, for example, different throttling conditions and many more. This will provide new boundary conditions for the 1D, 2D solver, which determines the performance of the turbine and pumps respectively. So we can see here the example efficiency and power output. We then receive these parameters like efficiency and pressure ratio, which are then automatically passed back to the cycle during the iteration process. This approach allows us to have a complete view of everything that is happening, not only on the system level, but also with accurate performance of everything at the component level without having to rely on performance maps. We can easily determine the loads on the bearings, for example. We can also easily determine if the secondary flow path provides the necessary mass rate at every state during the operation to cool the bearings or other equipment, for example. Additionally, what if or parametric studies can be easily performed this way. Let's say the user would like to change the geometry of one of the pumps in here. That can be quickly done by changing the respective parameters, the diameter for example. Conventionally, new performance maps would need to be created, which makes that process slow and complicated. The holistic approach allows a fast evaluation of the system performance and enables easy what-if studies.